All right, guys, so this is our review for the test for Unit 1. So it's talking about motion and kinematics, and we have lots of different motion, one-dimensional, horizontal, vertical, projectile motion, vector addition, so some circular motion, there's some moving down incline, so there's a great variety here. So the first one is just a velocity versus time graph. So it's a velocity versus time graph. And what you need to do is just access the graph and try to figure out the acceleration. So on the acceleration is just the slope of a velocity versus time graph. So it's the change in velocity over the change in time. That's what the slope would be, which is our definition of acceleration. So we're going to track the acceleration for different time periods. So from 0 to 2 seconds, it's a horizontal line, so that's really 0. If you wanted to do the math, it would be the change in velocity would be 0, or 10 minus 10 divided by 2. So that's still just 0. For 2 to 7, that's the next section, and I'll there to there. So I usually just count down how far it moves up or down. So it goes from positive 10 to negative 10, so that's a negative 20 meters per second, divided by how much time goes by. So from 2 to 7, that's 5 seconds. So if you do that math, negative 20 divided by 5, you get negative 4 meters per second squared. 7 to 9, there to there, it's another horizontal section, so that's going to be 0. I'm not going to worry about explaining that anymore. The next one, 9 to 11, so that section, so I need to figure out how much it goes up. So it goes from 10 to 0, so it's plus 10, and 2 seconds over, so plus 10 over 2 is a positive 5, it's meters per second squared. Another flat section or horizontal section, so that's a 0. And then finally, the last part, it's going from there to there, so it goes up, and it goes up 12, and it takes 3 seconds for that to happen. So it's a positive 12 divided by 3, which is a positive 4 meters per second squared. What we're going to do next is we're just going to take that information and plot it on a graph. So we're going to make an acceleration versus time graph. So acceleration is on the vertical axis. So if I make this across, make that my time axis, which is measured in seconds, that would be 0 for the acceleration. Acceleration is measured in meters per second squared. So we just need to pick a scale that fits our data. So it looks like negative 4 is our largest negative value, and positive 5 is my biggest positive. So I'm just going to count by ones, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5 negative. Okay. Again, positive and negative don't mean increasing or decreasing, it just means right line. For the time, we're just going to count 15. So 1, 2, 3, 4, like a bigger mark, and call that 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm 1 short, so I'm just going to make a little tick there and make it 15. All right, so we're just labeling this data, and we're just showing on the graph what's going on. So let me make this vertical axis like that. So that's my acceleration axis. And I did my time axis in black here. And I'm just going to trace with blue. So for the first part, it's 0. So I'm just going to stay at 0 for the first 2 seconds. So for the first 2 bars across, if you want to label that 0, you can if you're worried that it's not going to show up. The next one, it's at negative 4. So from 2 to 7. So I'm going to go down to negative 4. Negative 4 there. 5, 6, 7, 2 more past the 5. And that's that one. And again, you can put little dotted lines for the asymptote. 7 to 9. There. Positive 5 for the next 2 seconds, so that's from 9 to 11 is positive 5. It's back to a 0 for 1 second, 11 to 12, and then from 12 to 13, it's back at positive 4 across here. And again, I was shorted you 1, but that's the graph that you should make. And if you want to label them again, negative 4, 0, positive 5, 0, and positive 4. So you can label those, that's not a big deal. It's just to kind of display that you understand what's going on. So it's just shifting from constant acceleration to constant acceleration. The last part of this graph asks you to kind of figure out what's going on. So we're going to look back up here at this graph and answer these questions. So the first part says, when is it moving right? And you have to explain. So usually I try to do the explaining first and logic. So I think, okay, moving to the right means that it has a positive velocity. So I'm looking for any value that would be up here in this positive section. So kind of checking the times out here, it looks like it's from 0 to 4.5 seconds. If you just listed that, that's fine. You should only list one. The other one that is also good would be 12 through 15 seconds. And you could list like periods of time that fit that that range. So if you said 12 to 13 or 13 to 14, those are still positive velocities. Moving left is the negative velocity idea. So those are all the values that it's below 0. So that looks like it starts at 4.5 and it goes all the way to 11 seconds. So that's fine. Again, ranges or times that fit in that range are fine. So if you said 5 to 7, that's a good answer. Stopped, if it's stopped, the velocity is equal to 0. It's not moving. So that's anytime it's 0, so 4.5 seconds first time, and then it looks like 11 to 12 seconds would be the next. Then we talk about increasing, decreasing, and constant velocities. So an increasing velocity means the number for the velocity gets bigger. Decreasing, the number for the velocity gets smaller. And then if it's constant, the number for the velocity stays the same. So if we think about this, we can kind of list off time periods when that happens. So increasing velocity, another way you can think about it is the line moves away from 0. So if the number is around 0 or it's at 0 and it moves away, so I'm going to list my zeros here again. So this is my 0 that I just put in red here. I want the line to move away from that. So this section is moving away from 0. The numbers are getting bigger. The number for the velocity is getting bigger. It's negative, but negative doesn't mean smaller. It means left. So that's one decrease, or that's one increasing time period. So that looks like from 4.5 to, it looks like 7. That would work. Another one, increasing velocity, line moving away from 0. So that's 12 to 15. So those are good. For decreasing velocity, the line would move towards 0. So the number for the velocity is decreasing. So I'm gonna maybe change color and pick color that shows up. So decreasing, we're getting numbers closer to 0, numbers closer to 0 in those two purple sections. So that would be, it looks like 2 to 4.5. And then from 9 to 11. Finally, the constant velocity. So constant velocity is just a velocity where it is a horizontal line. So the line's not moving toward or away. So it's a horizontal line. This one doesn't say moving at a constant velocity. So 0 would actually work. So horizontal line. Sorry. So a horizontal line would include this section up here. So that's a constant velocity. So it looks like from 0 to 2, it's staying at positive 10 meters per second. You could just say that at positive 10 for the 0 to 2 seconds. Another section here, 7 to 9. That's at negative 10 meters per second. And then you could say 11 to 12 because it did not specify that it had to be moving. So it's at 0 meters per second. So its velocity is constant at 0. Okay. So that's basically what you're gonna have to do with the velocity versus time graph. I could ask you questions about displacements. I didn't on this review. So the displacement's just 1/2 PI plus VF times delta T. So you're just kind of looking at the graph, figuring out how far the object changed its position using that kinematics equation. All right, so we're gonna start to jump into some of the kinematics problems. So I think there's 6 or 7 of these on this review, so we'll try to get through it pretty quick. I'm at 10 minutes now. I might pause the video halfway through and stop it and make it 2 videos so it's not one super long. So this one, a physics student starts skiing down a frictionless incline. I'm just gonna make a dot for the student. That makes an angle of 8.2 degrees. If they start at 5 meters per second, so they're moving at 5 meters per second going down the hill, and they tell you the length of the incline. And in general, what's going to happen is that's going to go faster. So if you go down the hill, it's going to go faster. So that's a good picture because I have my dot with my 2 arrows. It's a slightly different situation, but it's still one-dimensional kinematics. It's just we don't have exact horizontal motion. So we got to use a little bit of the ideas that I taught you in class. So it says, what's the acceleration that they experience? So the acceleration on an incline, again, is just equal to g sine theta. So you're just going to plug that in your calculator. So it'd be 9.8 sine of the angle, which is 8.2 degrees. That's theta. So if you put that in your calculator, you get 1.4. So 1.4 meters per second squared. That is our one-dimensional constant acceleration that our student is going to experience. At this point, we can start to fill in a table because it's going to ask us for things like delta x, which it's horizontal. It's not exactly horizontal, but we're just going to tilt our head and imagine that it is. VI, VF, A, and triangle T. So going through the problem, we just found the acceleration is 1.4. 5 meters per second is the initial velocity, and it travels 120 meters down the incline. So in part B, it asks for how much time, or I'm sorry, it doesn't ask for how much time, it asks for what's the final velocity at the bottom. So we want an equation with final velocity that doesn't have time, so that's VF squared equals VI squared plus 2A delta x. So we plug into that, VF's what we're looking for, VI is 5, make sure you square it. 2 times A is 1.4, and delta x is the 120. When you do this math, VF squared turns out to be equal to like 361. And then you just take a square root of both sides, and you get VF is something like 19 meters per second. So that is what you should get for part B. So part A, the answer is 1.4 meters per second squared. Part B, 19 meters per second for the final velocity when it reaches the bottom. And then finally for part C, it says how much time does it take for them to complete the 120 meters? So we got this as 19, and now, that was part A, or B, sorry. Now for part C, we're trying to figure out that. So we can use any equation that has time in it. This is probably the simplest one, I think, to use. So we're going to G, sorry. All right, it's just A. And then triangle T. So 19 equals 5 plus 1.4 delta T. Subtract 5, do algebra, 14 equals 1.4 delta T. And then you divide through and you'll get the answer, which is just 10 seconds. So triangle T is 10 seconds. So there you go. There's the first question all worked out. Again, just kinematics. The only thing that's a little bit tricky is getting this angle, the acceleration on a ramp or incline. All right, so moving on. The next problem, this one's a little bit harder because it's a little convoluted. So we have this object or dog, so I'm just going to draw a dot for the dog. Starts from rest. So again, rest is good, so write the word rest. Has a constant acceleration for 10 seconds. So constantly accelerating means it's going to speed up as it moves. And I'm just going to make this the 10-second mark. Okay, so this is 0 seconds. At 10 seconds, it gets there. And it reaches some maximum velocity. It doesn't tell you that value. If it did, it would make the problem a lot easier. But after that, for the next 7 seconds, so I'm going to make this 17 seconds, the dog maintains that velocity. So this velocity here at the end of the first period. So I'll call this section 1, and this section 2. So this final velocity in section 1 is equal to the initial velocity in section 2. It's also equal to the final velocity in section 2 because this is constant velocity. This over here has a constant acceleration, but that just means it's increasing its velocity. So that's what's happening in these two things. So we got some time, so we got some ideas. It says the entire displacement of this dog, if I do that whole kind of delta x total, that's 240 meters per second, or I'm sorry, 240 meters. And if we break it up into the sections, so I'll get a red mark there. So this first section, I'm going to call delta x1, and the second section, which I'm going to put in green, that's delta x. Okay. So I think we have a good understanding of what's happening in this problem, but it doesn't seem like you maybe have enough information. So we got to come up with a couple of relationships that are outside of our standard kind of what's going on in a certain section. But let's start with those standard kind of information chart things. So for section 1, which I'm doing here, which I'll just put a 1 next to it, we got delta x1. So again, I'm just going to call that delta x1. We don't know how far that is. VI, we do know that VI1 is 0. VF in section 1, we're not sure about. The acceleration, we don't know. We do know that this is the time of 1, and that's 10 seconds. So we have 2 things. We're not sure about this. We're not sure about this, and we're not sure about this. So we don't have enough information quite to solve just using that part of the equation. If we look at the table for 2, similarly, I think we have some ideas, but not all of them. So this is delta x, which is going to be delta x2. We have the initial velocity in section 2, which is actually the same as VF1. So I'm just going to write this as VF1 because this speed stays constant throughout. So VF2 is actually the same thing. So these two are equal. So that might simplify a couple things because it like eliminates a variable. It just makes it 1 variable instead of 2. And then we have the acceleration of section 2, which is 0 because it's not speeding up, it's not slowing down, it's got a constant velocity. And we do know this time is 7 seconds. So again, it looks like we're a little short on information. So let's see if we can come up with any other relationships. And this relationship is going to help us solve what we need to solve for. So we know that if we add up the 2 sections of motion, delta x1 plus delta x2, we will get 240. All right. So I think the easiest thing to do is set up an equation to solve for delta x. And let's say we don't know this acceleration. So that's not going to be what we're looking for. So we're going to use the equation without acceleration. So no acceleration in this one. So it would be like delta x1 equals 1/2 the initial velocity of section 1 plus the final velocity. That's a I for 1. VF1 and then delta t. So, and that's delta t1. We don't know, well, we do know the time there. So I'm going to plug in the numbers that I do know. So delta x1 equals 1/2. VI1, that's just 0 because it starts from rest. VF I, the final velocity in section 1. And then this is 10 seconds. That's how much time goes by. So I can simplify that a little bit and get delta x1 is equal to 5 VF1. Okay. So that's not too bad. We have a relationship. We're going to use that later on and insert it up here in a little bit. For section 2, I'm going to use the same formula. Even though it's like the acceleration is 0, it's a constant acceleration. So I can use this same formula. So it would be for section 2, it'd be VI2 plus VF2 times delta T2. I left a little subscript of 2 there. Okay. So when we plug into this, delta x2 is going to say delta x2. These are the same, right? So that's 1/2, and I'm just going to write it in terms of VF1 because these are all the same. So VF1 plus VF1 is 2 VF1s. So we got these two are equal, so you get 2 inside the radical, and then it's or inside the parentheses, and then it's delta x2, which we already know that. We know that's 7 seconds. All right, so that's all right. So the halves and the 2's cancel out, and we just get delta x2 is equal to 7 VF1. So we're in pretty good shape now. I'm going to take those 2 ideas and insert them into the formula that we have a relationship between delta x1 and delta x2. So I have 5 VF1 plus 7 VF1 equals 240. So at this point, it's just algebra. So this is 12 VF1 equals 240. And now we're in pretty good shape. We divide through by 12. And we get the final velocity to be 20 meters per second. So the dog at the end is running really fast. It's running at 20 meters per second. That's the answer or solution to part A. Part B wants to know the acceleration in section 1. So we're looking for this acceleration. Now we know this velocity is 20. We could solve for the displacement, but you don't need to. We can just use an equation that doesn't have displacement. So if we do that, it's just VF equals VI plus AT. So if we plug into that, 20 equals 0 plus A, which we don't know, and 10 seconds is T. So we're just going to divide through both sides by 10 because the 0 goes away. When you do that, you get an acceleration of 2 meters per second squared. So those are the correct answers. If you wanted to check it, right, like you could go back in here and see if the numbers work out for what we did, right? So if we wanted to solve for delta x, we could plug in VF as 20 here. So half of 20 is 10, 10 times 10 is 100. So this should be 100 meters. And then for delta x2, we could plug in 20 here. So 20 times 7 is 140 meters. If we add those together, we do get our 240 meters. If you wanted to check it with the acceleration equation, you could do delta x equals VI t plus 1/2 a delta t squared. Delta. And you could plug in VI as 0, so that whole term goes away. This is still for 1. So it's 1/2 times 2 times 10 squared. So the half and 2 drop out. You get 10 squared is 100, which is the same answer we got up here. So that's 100 meters. The VF, it's the same idea. So we get the right answers and we check to make sure it was right. So that one's, again, a little bit more involved just because you don't have enough variables. So you have to come up with like another relationship, which is what we did there with the delta x. All right. A couple more and then I'll take a break. So we're getting into the position versus time graphs, so this x versus t graph. And it's just answering questions about average velocity, average speed, and then the velocity at a moment. So for part A, the average velocity idea. Okay. So the average velocity idea says that average velocity is equal to the total displacement over the total time. So we are looking for the average velocity for the whole 30 seconds. So our time in the bottom is 30 seconds. And we just need to figure out where we started. So this is our initial position, xi, and xf is at 30 seconds. So this is 30 seconds when we get up to here. So that looks like position E. So basically we're going from position A to position E, and we need to figure out how much it was displaced. So it would be the final position, which is 8, minus the initial position, which was -5. So the average velocity would be 13 over 30 meters over seconds. It's a positive value, and you should get something like positive 0.43 meters per second. So again, not too crazy. You're just finding the average velocity based on that equation, or it's the slope of the line that connects those 2 points. And I did a poor job drawing that in, but that's the right idea. For part B, it wants the average speed. So the average speed is the distance over the time, total distance over the total time. This time we're only going from 11 to 30 seconds. So 11 to 30 seconds, the difference between that would be 30 minus 11, which is 19. And then the distance, we're starting at 11 seconds, so we're here, we're going to here. So we're at -2, we're staying at -2, and then we go from -2 to 8. So that would be 10 for the distance. So it'd be 10 divided by 19. Put that in my calculator real quick. So 10 divided by 19 is 0.53. Oops, 10 over 19, sorry. 10 over 19 is 0.53 meters per second. That's positive. So that is the average velocity for that. I'm sorry, average speed for that. So that's part B, again, average speed. The last part here is just trying to find a velocity at a moment in time. So at a moment in time, at an instant, at 7 seconds, we want to know the velocity. And it's hard to tell exactly where 7 seconds is here, so it's hard to kind of get the exact right value for that. So, and that would just tell you the position. The slope of the line tells you the velocity. So the slope is equal to the velocity. So you just need to find the slope between points B and C. So the velocity, because it's constant, like these are all constant velocities. So the velocity would be the displacement over the time. So again, another slope kind of idea. It's starting here at -5 and going up to -2, so that's a gain of 3. And then over here, it's going from 5 to 11 over that time period, so that's 6 seconds of time. So 3 divided by 6 is 0.5 meters per second. And it would be positive. So that is the velocity at that moment, because all these velocities on this line is moving at a constant velocity, so they're all the same. Okay. All right, so I'm gonna do this last one here, and then I'm gonna take a break, and we'll be about 30 minutes, and I'll probably have another 15 or 20 to go on the next video. So the last one here says a ball is thrown upward from the top of a building, so ball going up. The ball's initial speed is going at 12 meters per second. What is the ball's final velocity? So we're going to assume the ball goes up, goes to the apex, and then it's going to fall downward. And it's actually going to fall down all the way to the bottom, like the ground that it starts at. So the ground 0, this would be 25 if you had your positions kind of labeled on the graph or position or picture. So going through the ideas, we're in the y direction because it's free fall, VI, VF, G this time, and T. So gravity we know is -9.8 meters per second squared. The ball is thrown upward at 12 meters per second, so that's a positive 12. 25 meters is the height of the ball, but the displacement of the ball or the change in position is starting at 25 and it's ending at 0. So this is like y initial, y final. So it's going to be a -25 meters. So make sure you put in the negative. If you don't, it'll come out to be something weird. So don't do that. You'll get a like negative value or something that doesn't make any sense. We're looking for the ball's final velocity when it's striking the ground, so VF. So we're going to use the one without time, which is the squared one for part A. So VF squared equals VI squared plus 2G delta Y. I said T, but it's delta Y. I said the right thing. There we go. And we're going to plug in the value. So VF is what we're looking for. It's squared. It's going to be 12 squared plus 2 times -9.8 times -25. You can see that if you don't put in the negative here, you're going to get a different value. So that's important. So you're going to solve that. This value on the right side turns out to be 634 is equal to VF squared. And like we did in the previous problem, we have to do square root to get VF. So VF is equal to, the numeric value is 25.2 meters per second. So that makes sense. It's faster than that because it's going to be going 12 here and it's going to speed up on the way down. The thing you need to decide is it positive or negative. So if we look at this arrow, when it's reaching the ground, which way is it moving? It's moving downward. So I'm going to put a negative sign here, and that's my solution for VF. Again, if you made it positive, it's not a major error, but it's going to show up in this next part where you're solving for time. So we can put -25.2 here meters per second. We're going to look for time in part B. So the easiest one that I think to use with time is this one. And VF is -25.2, VI was 12, and then we have -9.8 delta T. Again, be careful with your math. Make sure you subtract 12 from both sides. This is where it would become evident, like if you had, you would get a time that doesn't make sense, right? So anyway, you get -37.2 equals -9.8 delta T. Divide through by -9.8. When you do that, you'll get the time is equal to 3.8 seconds. So that's the last one. I'm just under 30 minutes, so I'm going to stop there, and we'll pick up with the rest of the review in the next video.